Hello calculus students, this is a little mini unit of review on sketching derivatives, but we're going to use the red-green show, which there was a video on before, and the flange slope meter. Now if you watch the video on sketching derivatives red-green show, great, but if not, do so now, because it goes over a lot of the ideas of increasing, decreasing, and concavity. Now I call it the flange slope meter because it's not your typical slope meter. Here's your typical slope meter. It's just something with a bubble in here like a level, and it can tell you the gradients or radians or degrees of pitch of the slope you're on. But now, we're hard to do that when we're on graph paper, so I considered making this slope meter. It's a circle of paper or cardboard that you use to quickly estimate the slope of a curve. And it's useful in estimating the slope off of a graph. And we're going to use it in conjunction with the red-green show. Here's the slope meter. Now notice the slope of -1. This is not the slope of the line coming through like this. It's the slope of the line that comes up against it. So if I were to draw a line here, like this, that line has a slope of -1. And the slope meter is telling you the slope of the line that it comes up against. Now, I've got many sizes here, so you can print this page and cut out the size you like. Some people like a bigger one because they can read the numbers better. Some like a smaller one because it's more flexible for using around on the graph. And this is what the summary of the red-green show is. Remember, we use red to look at change in the original function leads to sign in the derivative. And concavity in the original function leads to change in the derivative. So let's try our first example. Sketch the derivative of these functions. Now, as you can see in the handout I gave you too, there's some guidelines on for what you should look for, and that's, of course, max and mins. And right now we can spot right away that we got a relative max right there in the middle. See that relative max right there at the peak? That means you are going to have a derivative of 0. That's how the red-green show works. Right there at 2. So we can put in 1 point already. Point right here at 2, 0 on the derivative graph. Now remember that this is the derivative we're graphing down here, f prime of x. This is the original function, just f of x. Okay. Now, put this back because we might need that again. Oops, it's not right over there. There you go. Now, what about the increasing, decreasing sections? Well, we're clearly increasing over here. There we go. It's increasing this little section in here, and then it's decreasing. Decreasing all the way over here. So that means we're going to go from positive to negative on our graph. So we got a good idea already. It's also sad the whole time. It's concave down the whole time. So that means the whole time our graph will be decreasing. That's how the red-green show can help you come up with some ideas. Now, how the slope meter can help. Let's grab our slope meter from before. This looks like about the right size for us. Notice how the slope meter works. Let's look at this one over here. We touch it up against the curve like this and read off that you got a negative slope. It looks like about -3. Now it's hard to get real accurate. You can see how this doesn't seem to be touching and being tangent to it. You want to make the slope meter tangent to the curve there. So yeah, I could see anything, yeah, about in that -3 zone. It's not super accurate, but it gives you a rough idea. So that means I've got a slope of -3 at 4. So I come down here to 4, -3. 4, -3. 1, 2, -3. Let's check out that slope on the other side. I take the slope meter and put it up against this. Now it's hard to read on the endpoints too and so forth, but it looks like it's not quite as intense. And see, I needed to trim my slope meter better so I got a nice curve on there. You can do that really good with your slope meter. And I'm getting the slope more of a like 1.5 or so. Now be careful that you keep this horizontal line in your slope meter horizontal. This bar right here like this. If you start twisting your slope meter, rolling around, that doesn't work. So it's easier for me on this because it's automatically sliding it as opposed to rotating it. You've got to keep the horizontal and then touch it. See how up here, you clearly have that slope of 0. But over here, we've got a positive slope. And it goes from, it starts way up here at 0, and then it's going to get smaller and smaller and smaller. Or it's going to get bigger and bigger as it comes left here. So I'm going to hazard, see, 1 seems too big. You're trying to get the curve to match the tangent line to be just tangent. So let's say 1.5. I'm not going to be hypercritical on these. It's just to give you a rough idea of where the slope is. 1, 1.5. And then there's 3 dots we've got plotted. We definitely know the slope was 0 at that peak. And it's got to be decreasing. And you might as well just connect them with a straight line unless you suspect anything. The one thing we can't tell on a derivative from just the red-green show is the type of curvature this might have. Because you know our derivative here, this is f over here. And this is f prime. So the red part of the show tells us what the sign of the derivative is. Here, this is f and f prime again. The green part of the show tells us whether the derivative is increasing or decreasing. It never tells us, though, what the curvature is going to be like. That would be very tricky to do just from sketching. Let's see how we did. Oh. Not bad. Yeah, see, it looked like we should have gone with 2 for the slope there and -4 for the slope there. Our slope was not that far off, so I'm going to allow some flexibility then in where you estimate your slopes off the slope meter. Also, I think you're going to do a better job because you're going to trim your slope meter better. Mine was a little, need a little work. Okay, let's try this again. Decreasing section. A decreasing section right in here, followed by an increasing section. So what does that tell you about what's going to happen with the derivative? Well, it means on the derivative, and this is going to be our derivative graph down here, f prime, we're going to go from some positive slope to negative slopes. Decreasing to increasing. I'm so sorry. Got that backwards. When it's decreasing, we're going to have negative slopes, and then we're going to have some positive slopes. And this is what we call a sharp corner. So I'm going to get the slope just before and after that sharp corner. So you can see over here, when I slide my slope meter, I get a slope of 1 for this whole linear section. And over here, a slope of positive 1. So we actually get a whole region where we have a constant slope. Because essentially we had neither concave up nor concave down. This was a linear sections in here, so we're going to have a constant slope. So we get a constant slope at 1 over here, and a constant slope of -1 in this section over here. Which leads me to wonder what happens right there at the sharp corner. Right at the sharp corner. Well, what I want you to do is put a big open circle there, because the derivative is undefined at a sharp corner. The slope from the right seems to be 1, the slope from the left is -1. So you can't do the derivative there. So that just had to mainly do with the red part of the show. We had no concavity to talk about in this one. And George Bird agrees. Now here we see some concavity. And let's measure some of the key points. That is, any max and mins, and we seem to grab that max right there. So we see we got a relative max right there. That's going to be a slope of 0. So that's going to correspond to 0 on the derivative graph. Here's the original function. We also have a slope of 0 here. So that's going to be a 0 on the derivative graph for those relative maxes. Now this is a relative min, but you got to be careful though. It's also a sharp corner. So we're going to try and get the slope off of this from both directions. When we look at this sharp corner from this direction, it looks like you have a slope of -1. But from this direction, it looks more like a slope of +1. So we have this sudden change in slope here. Oopsie. Move the graphic. Oh, this 1 and this -1. That the slope coming from the left is +1, and from there is -1, and from the right is -1. I'm sorry, from the right it looks like a slope of 1. From this side it's a slope of -1. So we're going to make this sudden change in slope. Let's see how this jibes with our increasing decreasing ideas. Notice it's increasing up in here, so it's going to be positive. Then it's decreasing, so we're going to be negative. It's increasing, so we're going to be positive. And it's decreasing for a little bit there, so it's going to be negative. Now also look at the concavity though. It is concave down the whole time here, so we're going to be decreasing in this section on the derivative. It's concave down again here, so again we're going to be decreasing. Now let's finally get a couple more slopes here on the ends, just so we can finish our graph. And it looks like the slope here, if I look from above, is about, yeah, it's not 1. It's more like about 0.7. So we can plot our 0.7 slope here at the end of this point. 0.7. And so we can connect the dots on those. And then over here, it looks even shallower. And this is a negative 0.3 maybe. Or negative 0.4. So negative 0.4 when we get to the end over here. And we can connect the dots on those. Again, I'm not going to be picky about whether you've got this concave down or linear, because we really can't do that from just looking at the sketches. But you should get the right direction in terms of, I've made both these sections decreasing, because both these are concave down sections. And I went from positive to 0 to negative, positive, 0, negative. Let's see how that jibes with the big graph. Looks pretty good. And as you can see, I actually based this on a sine curve, but I put an absolute value to put a little kink in it like that. And right there at 3, we've got an undefined slope because of the sharp corner. Okay, flange out.